Now we will solve a problem on harmonic motion. Harmonic motion. You have a block on a spring. The spring is attached to the wall. This is ideal spring that obeys Hooke's law. F sub x is minus projection of force of spring is minus kx if I put unstretched position at the equilibrium. The surface is frictionless, and this is important, frictionless. And now I bring this block to the distance. This is unstretched position, x0. And what I'll do next, I will bring this block to position, let's say this is 0, to position x node. This is x node, which is a given number. We know x node. It's a given number. And this is still spring, which is now stretched. And the block is attached to the spring. So I bring it to the position x node on a frictionless surface, and then I let it go, which means that position at time moment 0 is x node, where x node is a given number, and I let it go, which means that velocity at time moment 0 is 0. What I want to find the position of the block as a function of time. So I want to know the solution for the position of the block at any time moment. And after we find that, we will answer a couple of more questions. But first of all, what is the position of the block at any time moment? We will start with the second law. Fx is max. If we draw the free body diagram for this block here, I will have gravity down, normal force up. And in x direction, what I will have force of spring. So force of spring is minus kx, and this is equal to max. This is not a good equation for us because we have x and acceleration both are unknowns, but we know how to relate acceleration and x. d2x by dt squared is ax. Now, this is the equation that has one unknown variable, which is x. m d2x by dt squared plus kx, and this is equal to 0. And this is the equation of simple harmonic oscillator. Famous equation. We need to know how to solve it. I will divide both parts of this equation by m, by mass, and I will have this iconic form for the equation for simple harmonic motion, d2x by dt squared plus k over mx, and this is equal to 0. We derived the equation that describes x at any time moment. Now we need to find the solution of this equation. So we will make an educated guess. We will guess the solution of this equation as a, where a is unknown constant, cosine omega t, where omega is frequency of oscillations, plus b, unknown constant, times sine omega t. A, b, and omega, that's what we need to find. We will find a and b from initial conditions. From initial conditions. Let's do it right now. X at time moment 0, x at time moment 0, this is my first initial condition, is equal to, I plug in time moment 0, cosine 0 is 1, so I have A. Time moment 0, sine 0 is 0, so this guy is equal to 0. I don't even write it. A is equal to x naught. We found A. Now we need to find B, and we will find B from the second initial condition. Second initial condition is for velocity. We know that velocity Vx is dx dt. We need to take the derivative. So velocity is a function of time. Velocity is a function of time. I differentiate x and I get minus a because derivative of cosine is minus sine omega t. Chain rule gives me omega. Now plus b. Derivative of sine is cosine omega t. And chain rule gives me omega. This is velocity at any time moment. And now I will write velocity at time moment 0. Velocity at time moment 0, plug in 0 here, sine 0 is 0, cosine 0 is 1, so I have b omega here. And this is equal to 0. Velocity at time moment 0 is equal to 0. We can add x projections, but since it is 0, doesn't matter. Which means that b is equal to 0. We found both arbitrary constants, a and b. A is x naught and b is 0. All we need to find is omega. How to find omega? We take our solution. In our case, it is x as a function of time. It is x naught cosine omega t. It's now shorter because b happens to be 0 with our initial conditions. And I plug in this solution into my equation. First of all, I need second derivative with respect to x. What is second derivative with respect to x? First derivative, we already did it here. This is first derivative. And second derivative, I just need to differentiate this guy one more time, and a is x naught. Second derivative will be minus x naught omega. Derivative of sine is cosine omega t. And chain rule will give me another omega. So this is d2x by dt squared plus k over m x, and x is x naught cosine omega t, and this is equal to 0. This is my equation. Now I simplify it. I divide both sides by x naught. I divide both sides by cosine omega t. What is left? Minus omega squared plus k over m is equal to 0, which gives me omega squared. Omega squared is k over m, or omega is square root of k over m. We solved the problem. Now what is x? X as a function of time at any time moment is x naught that was given. Point where we bring our block at time moment 0, x naught times cosine omega, where omega is square root of k over m times time. This is x as a function of time. We answered the first question. By the way, this, if you solve a slightly different problem, but rewrite it the same way, second derivative goes first without coefficient, then coefficient times variable. This will be always omega squared. So k over m is omega squared. Now I want to answer another question. And my second question is, what will be, sorry. Can we pause for a second? Now I want to answer second question. And my second question is, how long will it take for the block to come to equilibrium? How long means time. So what do we know about the point when the spring comes to equilibrium? At the equilibrium, that's our choice of coordinate system. At the equilibrium, x is 0. Let me erase this. So one more time, what are we doing now? We are finding time that it takes to return to equilibrium to this point. What is this time? X is 0. So I'm looking at x when x will be 0. The first time when x is 0, cosine is oscillating. When cosine will be 0. Cosine will be 0 when k over m times t is equal to pi over 2, which makes this specific time for the block to return to equilibrium as pi over 2 divided by k over m, or square root of m over k. This is time to return to equilibrium when x is equal to 0, which means the first point for cosine to be 0, which is argument of cosine is pi over 2. And the last question that we will answer, what is velocity of this block when it is at equilibrium? The velocity of this block, we can find the velocity, we already have the formula for the velocity right here. It's derivative of position. Now we know that b is 0. We don't need this part of velocity. We have just this one. So when it is at equilibrium, it means that velocity has its maximum value. This is one way to understand it. Remember, conservation of energy, so it is moving. When this block is at equilibrium, it will be moving with fastest velocity, so we can just put sine here to 1 to find maximum value, which will bring us to v sub x as minus a is x naught times omega. This is one way to think about it, and it is projection is negative because it is moving to the left. Another way to think about it is we already know time. Why don't we take this time? We already know that square root of k over mt is pi over 2. So square root of k over mt, this guy is pi over 2, which means same as we just did, we put this to 1. This is pi over 2. The argument is pi over 2. Sine pi over 2 is 1. And v sub x is minus x naught times omega. Where omega, we already found it. Omega is square root of k over m. So it will be equal to minus x naught square root of k over m. I remind you that we started with the second law. We wrote the projection of second law in x. We connected acceleration and x using definition of acceleration. We derived this equation for harmonic oscillator, second derivative of position with respect to time plus constant position is equal to 0. We wrote a guess for the solution with 3 unknowns, which are A and B that we found from the initial conditions that were given. At time moment 0, the block was at x naught and velocity was 0. And then after we found A and B from initial conditions, we found omega frequency of oscillations by bringing our solution, our guess of the solution into the equation. And this is omega, square root of k over m. And then when we know x, we found all possible questions. How long does it take to come back to equilibrium? What will be the velocity at the equilibrium? We answered all these questions.